So we were doing logistic regression, and we left off here. Yeah. When I tried to show how we can use the tokenizer, which was a transformer. Now it has a dot transform in there. Same goes for remover, for stop remover. And we said we have also one more, which is the count vectorizer, and we call it counts. But we know that we need to call the fit function on it. So how can we do that? To see if we can create this new column in there. So we were able to create this tokens column in the first stage. Then we created the second column, stop word free, in the second stage. And those were through transformers. Now we want to create the third column in there, where basically we want just the output from this count vectorizer. So how can we do that? So we have a fit here. So if we do dash this, and then we run this, what happened? Nothing. So transform df2. No, actually, it's not working. Oh, sorry. Yeah. So now we see that we created the third column in there out of that estimator. Now we can show that. And this is how it looks like. Basically creating this last features column, which is basically a sparse representation of that data. That's what we want. So when you stick those through set stages inside that pipeline, that stuff gets done for you, basically through the pipeline API, right? All right, so now we know that we have 1, 2, 3, 4, 5, and then we want to use 1, 2, 3 as being negative sentiment, and 4, 5 as being a positive sentiment. So the first thing we need to do is basically to create those two classes. And one way of doing that is using something called the binarizer, right? Where basically we set the threshold to be 3.5. So anything below 3.5 would be considered negative, and anything above that would be positive. And that's what we're doing here. But that's not the only one. What if you want more than two classes, multi-class classification, which wasn't supported up until like last December? In this case, then what we do is we use a bucketizer instead, which is kind of like a general form than the binarizer. And what you'll have to do is you have to pass in your split points. Basically, you create the split array, the array of the splits, in this case 0, 3.5, and 6. And then if you pass that to the bucketizer now, anything between those thresholds will be a different class. So in our case here, we are using this, the bucketizer, the binarizer, I'm sorry. We again split the data. By the way, I wanted just to mention, somebody made that remark to me earlier that probably when we did linear regression, the results were not that correct just because we needed to normalize or standardize, you know. I mean, there are things, that's probably you need to do when you're doing like machine learning, like things like normalizing and removing the mean and all that stuff. So we're not doing that stuff in here, but the idea and the goal here is really not to do machine learning as far as show you how to use SparkML API to do that, right? But the possibility is there to do all that stuff, like normalizing the data and all that. Okay, so here we are basically splitting the data and then caching it as we did before. And I can go ahead and create the logistic regression component, and I create the pipeline as I did before. So by this time, if you feel like bored, that's a good thing. Because if you learned something so far, what we learned from how to do machine learning will be just a repetitive task, right? So we used it for linear regression. We will use it again for logistic regression. We will use it again for decision trees, for random forests, GBT, gradient boosted trees, whatever. It's going to always be the same API. This is actually by itself a very good thing on Spark, because when they designed the API for the data frame slash data set, obviously when I say data frame, it also means data set, they try to not change the API and keep it the same as much as possible. And the reason behind that is that you don't have to learn more stuff each time you switch from one block to the next. If you are familiar or used Spark Streaming before, which uses RDD, the way it works is you have data that's coming in the pipe, and then you define your batch interval, say like every 1 second, give me something, give me an RDD. And then it will give you Spark Streaming will give you an RDD, and then you go into that for each loop, and then you do something. In structured streaming based on data frame, they changed all that. And if you look structured streaming, it's exactly as if you're working with the plain data frame API. So it's df.read, and df.save becomes df.start if you're using Spark structured streaming. And once you have the data frame, then you can just use it as if you're using any other data frame. So they try to keep the API the same, whether you're working out of graph frames, or you're working out structured streaming, or you're working out ML Spark ML. So that's the idea now. Let me make sure this thing stays on. Okay? So now what we did, we created a logistic regression component. We created a new pipeline, and then we called the set stages on it, basically to just stick in there the tokenizer, we know why, the remover, we know why, the counts, we know why, and then the binarizer, we know why, and finally we call the LR on it. And once we set up the whole pipeline, all we have to do then is basically to train it. Any questions so far? Is it straightforward on how to use Spark ML? Okay. So while it's doing something, let's see what happened here. We can look underneath here and see what's going on. While it's working, I wanted to show you something here. If you look under the DAG visualization under the Spark UI, which runs under port 4040 in here, if you're using some other stuff like Yarn, for instance, usually you go to it through from 180AD, from the resource manager or the history server, and you navigate here. You can see here we have blue stages and green dots in there. Green means that they are cached. If they are not cached, they will be black. So if you have something that's already cached and you want to remove it from cache by calling the nPersist on it, the dot will turn into black. Another thing that also you need probably to know is when Spark does the shuffle, it saves those that shuffle information as shuffle files, right? And then that's like optimistic cache, which is not accessible to you, but Spark uses. Now, if next time you want to use shuffle and then Spark sees that those files are there, it will just reuse those files. And the way you know that, if you look at the UI, those blocks, they will turn gray instead of blue, right? So if you look at the UI and see the gray blocks in there, it means that those are skipped, basically. Shuffling was skipped for you. So those things probably it's good to know. Another thing that I wanted probably just to mention here, even though it's a machine learning class, but I think this is kind of like important stuff to know. If you look at the UI under stages, you'll see this event time. And in there, it tells you green is CPU time. So this is really what you're shooting for here. You should see a lot of green in there. Shuffle right, shuffle read, you try to minimize those, because those are kind of like, that's what makes code non-performant. And serialization, the SERDs, meaning like saving data to memory and deserializing the data from memory. When Spark started, it was using just Java objects, and those are fat objects, they're bad. Basically, if your payload is like 10 bytes, you will end up with like 65 bytes just as for overhead, because you're sending all the metadata along with that. Then Cryo came along and improved the performance a lot there. And then, better than Cryo, we have now Tungsten. Basically, that's what the Catalyst uses as well. And in Tungsten, basically, it's just binary data, the payload that's being compressed. So if you have a file, like 200, 250, whatever, and then you cache it, and you look at the UI, you will see that it consumes less than that. And that's given to you by Tungsten being like a good compression scheme. So that's the stuff that probably you need to look for. So let's see if it's done. Okay. And now it's telling us that it's 0.90 for the area under the curve and the rock. But this is for using the training data, though. I mean, kind of like misleading, because you can do that. Really, we need to look at the test data and what we get out of that. So let's try it on the test data and see what we get. Now that we have the model, and because the model is itself a transformer, all it does is take in a data frame, gives you back a data frame, and we are using the data frame input here is really the test data. If we call the binary classification evaluator on it, it gives us an AUC of 0.84. So it really dropped from 0.90 down to 0.84, because that's the value you should look at, because that's the test data, basically, not the training data. Any questions so far? The display function that comes from Databricks has also the ability to graph the rock curve. And so if we do it here, the only thing is that we'd have to run it through. So prep data will just fit in the training data, and then we're transforming it again. And then if we call the fit on the logistic regression, and we call display, we should see graph here. Okay. So this is the rock curve. And then if you go around here, you see the threshold, and then it gives you kind of like an idea how it looks like. This is using a logistic regression. And this is how you can use things like display to look at that stuff. We can do explain again, which gives us some information about what's there for default values that you can also change. And you can also play with these parameters, and it's a good time for you to try it and see if that changes a little bit. And then once you do that, then we'll move to the next one, which is the decision tree. So let me give you like a couple minutes to try that, and then we'll move to the next one. Yes?
How do you get the area under precision recall curve?
I'm sorry.
How would you get the area under precision recall curve?
So just by calling the display function. Yeah, because it's embedded in the display function. By the way, these accounts will expire in a month. So basically, you have a month to play with the code in here or even move it to your other accounts. But you're more than welcome to create free accounts and then just export this code and then re-import that in those new accounts. Okay. Let's see. So what I did change here is basically use 500 instead of 1,000. So less probably expect to see worse results than before. But this is just one of the parameters that you can play with, obviously. This is what I was talking about earlier. See, because this stage was all skipped, then those blocks turn gray instead of blue. So when you're looking at, thank you. Thanks. When you're looking at the UI, you can tell whether shuffled files are being used or not. Okay. And it's 84, no change mostly, right? Okay, so let's move to the next one. Any questions so far about logistic regression? Okay, so let's move to 60, which is still a Scala notebook, but you can also do it in Python. In this decision tree, actually, we have 20 news groups in there. And we're trying to see if we can classify them using a tree, right? So again, we will read the input data here as a Parquet file, meaning like we don't have to worry about the schema because it comes in from Parquet. And then we can even display some of it here. And this is how it looks like. We have an ID column in there, text column, and then a topic, which probably we should keep, and a final column in there called label. Probably it's kind of like useless. Yes?
In the previous topic, we were planning the sentiment analysis as well?
Yes, actually, that's what we did. Basically, using the text, we tokenize it as word, and then we're trying to use each word, whether it can give us that information, whether it was positive or negative as a sentiment analysis. And when we use the test data out of that, it gives us a precision of like 84%. Like that was the yes, yeah. Yeah, he was asking, how did you do to measure the sentiment analysis there, right? I mean, in the previous notebook, because we were doing like negative versus positive. And what I told him is that when we used the test data and then we measured the precision, we saw that we were able to accomplish 84% given the words in the test data, right? Because each word now will tell us whether it's going to be a positive or a negative feedback, right? So this is really not a true sentiment analysis per se, but it's just a good example to show you how you can take an NLP case and turn it into a classification problem, right? So remember I said the data frame now has the schema on top of the data, and as well as the data set. And this is how you would look at that schema, basically. Just call the print schema API, and then you can see in there that you have string double, right? We see a double in there because we have a true schema that's coming to us from Parquet. So let's assume we're not using Parquet, we're using CSV, and then we don't provide the schema. Then what happened? Spark will read everything by default as string. Right. So even if your data is double, or let's say you have geolocation data, it will be read in as a string, and it could be null if you can find a value for it. So what you usually end up doing in such a case is to go through that and then kind of like recast the fields that you know to the types that you know they should be casted to. Basically, that's what happened. This is something that I've seen also done in Spark streaming, when let's say you have a Kafka server sending you stuff, but then let's say you are not aware of the schema. In a non-production environment, what you can do, let's say you have like a Kafka server sending you the stream, and then you have like a TCP server sending the same data, you can read like one line from the TCP server and try to infer the schema there, right? And then modify it even manually if you want. And once you have that schema built, then you can just grab it and then use it with the Kafka streams. Basically, just stick the schema on the Kafka streams, and then you start receiving the data from Kafka, basically. Same thing goes for Kinesis. Very similar when it comes to functionality, except that one is free and one you have to pay for. Okay, so here we are looking at examples of how we can drop label, like drop columns. In this case, label kind of like useless, we don't even need it, right? So this is one way of how you do that, basically. You just drop the columns that you're interested in this case, label and ID. And then we want to rename the column that's called topic, because we want to keep it. We want to rename it as label, and that's what we just did. Here we're looking at the first line. But as you can see, I'm using this kind of like weird looking syntax in there. So I am selecting, so corpus df is a data frame. And I can do anything I can usually do using SQL, I can do using the data frame API. So if I'm doing a select star, it will be a dot select using the data frame API. I'm doing a where clause in SQL, I would do dot where. Right? So if you are familiar with SQL, which I'm sure you are, then it will be like very easy to move from the data frame API, the SQL, to the data frame API and vice versa. By the way, usually I ask this question like which one is better, whether to just use plain vanilla SQL or use the data frame API. And some people, they may go like, oh, maybe data frame API is better because it's more performant, right? It's better because of performance. And that's not true. Because whether you're coming from data frame APIs, or you're coming from plain vanilla SQL, or you're coming from a data set, once you hit the catalyst, it's the same thing. Right? So it's really a personal taste now, how you want to proceed with this. There are people who want still use the SQL, but you know, if you have complicated subqueries in there and all that stuff, it becomes tough to take care of it, or at least have it like you know, an easy way how to look through it instead of just using the data frame API. So I find that usually the data frame API is better than plain SQL, but you know, it's really a personal taste here. So we're using as string, because we are casting it to a data set. So basically, we want to see it as a capital S string in there, as a class string. That's why we're doing it that way. And nothing happens in terms of like computation under the hood, or Spark is not doing anything, just giving you a new view over your data. So you have this capital S string, and then you can also call it with lowercase string. You will have both versions in there. But in this case, we are casting it as a data set and just looking at the first value in there, which has a lot of probably metadata that you need to take care of. So, so what do? First thing, we tokenize the input. Right? And then there's something we haven't seen before, set min token length, because that's also useful sometimes. Like, when you're tokenizing something and maybe anything less than 4 characters is probably not even important, then probably you can just throw it away or ignore it. In this case, we are doing just that. This is something that probably you do also when you do topic modeling using LDA, latent dirichlet allocation, right? So that stuff, you find it everywhere, whether you're doing NLP or you're doing LDA, whether you're doing just like in this case, we're just doing like decision tree here. So we call the transform on the tokenizer because the tokenizer is a transformer, right? We can display some of it, as we saw before. And this is how it looks like. And then we do the stop remover, but this time we are providing our stop list, basically. So this is where one exists under mount training. We have our own list, which we do use through collect. So collect is an action. It's a driver action that you need to be careful about when about using it. So because when you do collect, you are basically bringing all the results back from the nodes back to the driver. And if you have a lot of data, then you're going to kill the driver. Right? So you got to be careful there when you use collect. So in this case, it's a small list, and this is how it looks like. And then we just go ahead and call the stop words remover, but this time we are passing the list, and then we're setting the input and the output columns, and then we're calling the transform on it again because it's a transformer. That's what it is. Yes?
Right now you're dealing with strings and some data types. What are the data types? Like when you're getting a CSV file with names,
Yeah.
you want to treat them differently. Are there certain things you can do which are specifically with date functions?
Yeah, what happened when you have date information in the input source, and then you read the file into Spark? Is there a special way of how you deal with that data? That's the question. Yes, I mean, you can read the timestamp data as string, and then what you do, you can cast it later on as a timestamp. And then once you cast it as a timestamp, then you can just use like Java date format functions on it, like to extract the month or extract the year or do anything you want to the timestamp information. Yes. Yeah. So if we look at the filtered data here, we can see that from has been removed from the tokens column. We see it clearly in the filtered column that from, at least it's too bad we just only see from here, but they are all gone in there. And the next one is, because this expect a double value, right? And then we have like some text as labels, then we can use this string indexer, kind of like to convert it to a value that we can use later when we do the decision tree. This string indexer, and then I introduced it this morning, if you remember. That's the easiest one, by the way, if you want to look at the code and then try to understand how the estimator works so that you can add your own estimator later, right? This is probably your best bet to understand the code with this one here. So in this string indexer, what we're doing is basically counting the frequency of that label and then assigning the lowest index to the most frequent one, basically. So if you have an example like A, B, then A will be assigned index 0, and then B will be assigned index 1. Things like that. I'm sorry. Huffman coding? No, it's not that complicated. No. Yeah, it's a very easy mapping, actually, between the frequency of how many times. I mean, no. Huffman coding is this plus a lot more, right? So, so once you have this labels all counted out, and then the frequency mapped to indices, then you create this new column called indexed label. And then we have this call in there to set handle invalid to skip. Anything that we don't know how to do it, we'll just basically skip through this string indexer. Now, as you can see, we are calling the fit function on it. Why? Any idea? Because it's an estimator. Right? It's a complicated component. So sometimes when you need to bring data from different places, then it becomes an estimator because it's harder to implement, right? So in this case, string indexer is an estimator. So we create this label indexer. If we print the schema again, we can look at what we did. We added this filtered column in there. And then we no longer need tokens. So usually when you see that you don't need columns, just drop them. Don't carry them around, because it just going to make things look complicated. So once we have this string indexer in there, we can just call the count vectorizer as before, which is itself an estimator. And then we split the data as we did before between 80% and 20%. And then we call the decision tree again. So if this looks boring, that's a good sign, because it means that it's the very simple API that doesn't change, right? So whether you're doing decision tree or supervised, unsupervised, it's exactly the same, right? I mean, you spend most of your time doing pre-processing steps, and then which are very shared a lot between the different algorithms. And then at the end, even if you go for different algorithms, whether they are like supervised or unsupervised, the way you call them is the same. That's the idea here. So in this case, we're creating a decision tree classifier, and we are setting the index label, and then we are setting the feature column, and then we are setting the depth. So if we didn't call this set max depth to 16, the default one will be around 5, which is not good. Right? So if you just use the default, it's gonna probably be a bad choice. But I don't also like this way of doing things, because here we're kind of like cheating here, right? We're setting it to 16. We're basically using we're biased, right? We know that probably 16 will be a lot better than 5, then we set it to 16. But this is not how you would do it normally. You would let something like cross-validation do that for you, right? Now we have this convert index labels back to original labels. So index to string is the reverse of string indexer. So when we had like, if we have a label, right? Something like, I don't know, like computers, and then we map it to a value, let's say 0, most frequent one, 0, and then we do some analysis, and then we want to go back to computers, then we're going to get lost. We don't know how to map back to that. This guy, index to string, will give us that functionality, right? So it will allow us to go back to what we had before, so that, it's going to be like human-readable labels in there, so that we can understand what we're doing. We can use such a thing like when we're doing clustering, for instance, like k-means, instead of having clusters being numbers, we can have them have labels, right? Things like that. So this is where index to string is used. So once we create all that stuff, let me start this so that while I'm talking about this. So once we have all those components, again, what we need to do now is to create the pipeline, right, as we did before, and then call the set stages on it. So we set the label indexer, we set the vectorizer, we set the decision tree, and then back the label converter, right? And then we call the fit function on it, and we train it. We train it by passing the training data to it. So what we should expect back, we should expect to see a model, which is a decision tree in this case. A decision tree that has 16 levels for depth, So that's probably the most important parameter to tune through cross-validation. Because if you just let it go deep, then probably you're going to overfit very quickly, right? If it's too small, then probably it's not going to do a good job. So that's where cross-validation comes in and then help you tune that parameter. So while it's doing that, I would like to emphasize the point that I mentioned earlier when I said, like, once you read something from the source, you are basically following what the partitioning scheme is coming to you from the source, if it's HDFS or Cassandra or S3 or things like that. Now, once you have the data, you can always repartition the data, obviously. You can either go down, like usually what we do in Spark streaming when you have to do coalesce. You go down in the number of partitions, then basically you just coalesce down. Or if you want to repartition under a few parameters, then you can always call that repartition parameter. But if you don't do anything and then you inject something there that it uses shuffling, then 200 will be the default number of partitions. So if you are running something and then you look under the hood and you see the 200 number, then now you know why. It's a default value that comes with Spark. You can change it through that conf variable, but it's 200, which happens to be a good value for a real cluster. But for this type of clusters, like 8 threads or whatever, 16, it's a big number. Right? Okay. Any questions so far? Okay. All right, so we can print the stages. Like in here, each stage has an index or an ID. And then we can look at the stages. We can recognize that we're doing string indexer. We're doing account vector, vectorizer, decision tree, and so forth. And then finally, we call the transform on the test data. What is it? I'm sorry, I couldn't hear you. Okay. Now we can show 200. Now, if you don't use 200 in here, the default is 20. So you just issue like show parentheses is going to give you 20 by default. So you can control that. And in here, we can look at this, and right away, we can see that this is not good, right? Like this label was predicted as, yeah, well, this is not a big deal. This is problematic, right? Yeah, this is kind of like way different, right? So that's where cross-validation comes in, kind of like to tune the tree. Now, this is one tree. This is this decision tree, one tree. Now, it has been proven that ensemble techniques work better, obviously, right? Because big success out there. Random forest, unfortunately, there's nothing that's covered in those notebooks that does random forest. We will see GBT, gradient boosted tree. But those guys like random forest, they work better because the way they were implemented, even though I think that they still don't understand why they work. I mean, no mathematical explanation behind them. It's not like SVM, support vector machine, where we can prove mathematically why they work. In random forest, they work, but we can't prove that, mathematically at least. But the way I think why they work is because of the randomness injected when you are basically subsampling from the data all the time, and the fact that you are also randomly splitting at the split points. And instead of creating one big tree, as we did here, which tries to capture all the information in the data, instead, what we do when we do something like an ensemble technique like random forest, we create weak trees. We call them weak learners. And each tree is just trying to learn one part or a small part of that big information. And then at the end, instead of having one tree, we end up with many, many trees. And then if we're doing a regression, we just average, and we're doing a classification, we vote, basically. That has been proven to be working very good, at least, you know.
I think this model says you exclude all the word less than 4 or less.
Do you have a mic? Do you have a mic around? Can we use a mic? Oh, we don't? Sorry.
So this model, you exclude all the words that is less than 4 character long.
Yes.
So that is the issue here.
Oh, it is there? Oh, that is the issue. Why it's not working?
That's why the performance is bad.
Why the prediction is bad? Why is that?
Because you excluded all the words that is less than 4 character long.
Yeah?
So there could be some of the word may associate with the domain, but since you excluded from the training set.
In this data set, we don't care a lot about those 4 and less. Just because we're using like big names through those the news groups. So that's not the issue. Yeah. They're kind of like noise, actually. Right.
But in this case, talk is a word. Here, okay, dot religion.
Yeah, but it's the whole thing. It's ALT. Am I missing something there? It's ALT dot atheism, which is the whole thing. Not just the 4 characters, not just ALT. You see what I mean? Yeah, I'm not looking just at ALT, I'm looking at the whole thing there. Yeah. So in this case, in the one tree case, we are trying to capture all the information in the signal in one shot, which is kind of like hard to do. I mean, we can tune it, obviously. You know, we can probably make it work a lot better, but still, I think that random forest will be a lot better just because we're not capturing with one tree, capturing all the information. With many, many trees, we're trying to capture those weak learners are trying to capture information all along, and then we average or we vote at the end. Okay, so for the evaluator, we do as we did before. But there is one thing that's new here that we haven't seen is this thing here, the tree model that dot to debug string, which will allow you to see the output from the tree, right? So you can, it's hard to follow here, but you have the option there, basically to print the output of the tree. I think there's also, if we just take this, I think it's going to work. Usually when you try something on the fly, it doesn't, but we'll try it. So if I do display, and then I give the model's name, display should have something, yeah, here we go, which is probably not that great, but it works. You know? So display has this function that when you pass in a tree to it, it tries to display it as a graph, basically. So if your tree is complicated, then it's probably nonsense to make to look at it anyway. But the option is there. That's it. Any questions? Questions about Spark in general, not just machine learning? Yes. Yes, through pipeline, yes, you can. So now you're talking feature engineering, right? So basically, you're trying to, is it output after the output or before the output? You can. I mean, technically you can through the pipeline. Now, from a machine learning point of view, I'm thinking like that could be problematic because that will fit under data snooping. Yeah, no, because you are biased. You know what you're doing. You're helping the model in some sort, and that's bad, right? If you're helping the model, you should probably not do that in general when you're creating a machine learning model. Basically, try to stay away as much as possible from impacting the decision on the model, right? Because if you look at the output and then you feed it back, you just called it like what? Physical feedback, positive feedback? That probably can impact the model. But if you can do it, yes, through the pipeline, because you just stick the stage in there, right? Okay, so let's move next to number 70 under this here. So this is the first Python notebook that we will do. But I'm going to ask you to do it, basically, and probably just give you like whatever, like 20 minutes or so to do it. But this one here is really summarizes everything about machine learning on Spark, right? So it uses, it's an easy data set. So what are we trying to do here is the data set contains bike rental from 2011 to 2012. And we are trying to predict, right, the rentals and all that stuff. We want to learn to predict bike rental counts, basically, per hour. So it's an easy data set, right? Yes?
By the way, I tested this gentleman's theory by using the 4 characters to that really did work.
It didn't?
It did work.
Meaning?
Lot more of the atheism work.
I'm sorry, I have to get closer to you.
I said I tested the theory by using the number of characters to do, and it did worse. The tree did worse.
Oh, okay, so it was better or worse?
Worse.
Worse, okay. So you're confirming that thing works, the 4, right, thing. Okay, that's good.
Could you repeat the question?
Yeah, he says that he played with that minimum number of characters, because in my case, I set it to 4. He changed it to be 2. And then the results were different, obviously, and even worse, right? That's what he did. So that's a good thing, actually, because now I hope you can see how easy it is to change those parameters on the fly when you're doing something like this on Spark. This used to be very hard to do when like in the Hadoop time, like through Mahout, for instance. But just because Mahout didn't support all those sophisticated algorithms, at least back then, because now I think Mahout runs on Spark. So, but definitely we're making a lot of progress when we do machine learning in parallel. That's another thing that we will look at a notebook later for scikit-learn, because a lot of people ask, how can we mix scikit-learn with Spark? Because they just know how to use scikit-learn. Scikit-learn is the best out there. Probably sorry for the R guys. And it covers a lot of models in there, easy to use, all that stuff. But the problem with scikit-learn is that you have to still do it on one node, basically, to create the model. So the way scikit-learn works with Spark is you would create the model on one node, and then you would parallelize the cross-validation. Because really, cross-validation can be easily parallelized, right? So you would create the model, then you will send that model to all the nodes, and each node will try it on its own part of the data, basically. And then that will help in the final selection of the model. So in this notebook here, you're going to try to predict the bike rental counts per hour. It's an easy data set. You will be using basically you will be using all the components we saw before, the pipeline, the dot fit on the pipeline, and also what's important, you're going to be learning how to do cross-validation. So in here, we will be using the vector assembler. We saw that. Vector indexer, which is similar to the ones we saw. And then you're going to create this cross-validator pipeline, which has a fit function, fit API. And inside that pipeline, in this case, we're sticking another pipeline that has the GBT in there, the gradient boosted tree. So we're going to be using an ensemble technique. Instead of a tree, we're going to be using an ensemble technique. In this case, it's GBT, right? So we'll stick it in there, and then you will learn how you can pass, because the cross-validation now needs two things. It needs what it needs to tune, in this case, the GBT, and it needs the parameter to use, which you will provide through a grid search. So there will be like no code that you need to come up with. Just the code is there. Just run it and then try to understand. It's very well commented in there. So when we're trying to do cross-validation, for those who don't probably not familiar with cross-validation, it's first of all, we are in a supervised world now that we can use cross-validation. And the way it works is, let's say we reserve 80% for training, as we did before, to create the model. And then we reserve 10% for testing the model at the end. And then we reserve 10% for cross-validation. And once we create the model, we test the model, now we're happy with our model. But still, we can still tune those parameters or hyperparameters, right? Like if it's a line, I'm talking about beta 0, beta 1, basically the intercept and the slope. So we use cross-validation to tune those for us. And the way it works is we take that 10%, and then we will split it into parts. It could be 5 parts, or it could be 10 parts, or it could be even different number of parts. Usually, what people do is use 5 or 10. So 5-fold cross-validation or 10-fold cross-validation. And then we will use one as a test, and then the remaining as a training. And then we will loop again, and then we will use another one as test, and the remaining as training. And then we keep doing that in a loop, basically, until at the end, we pick the best one that gives the best results. Randomness is also used during cross-validation when you do the first split up. Basically, you can just use randomness in there. So basically, that's what we're going to be doing here. So why don't you start on this one? Let's pick like 20 minutes, and then we'll talk about it. And please, if this cluster is not running, then please just go ahead and create a new one. So let's go over this one here quickly. Hopefully you saw how you can call this cross-validation, set the grid search for the cross-validation, and how you can call the GBT, which is exactly the same as when we called the logistic regression, linear regression, and all that. As you can see, we're still using SQL context in here. But you can later, as an exercise, change it to use Spark if you want. That shouldn't be difficult to do, because now SQL context is embedded within Spark, the entry point. So I'm displaying some of the data in here to look at it.
I have a question.
Yes.
The SQL is embedded Spark. Nested SQLs also. I remember the previous version of Spark.
Nested SQLs, you mean subqueries? Yeah, support for it is getting better. Let me put it this way. So a year ago was very painful. So it's getting better. Yeah. Huh? Yeah, he asked me how is subqueries, the support for subqueries on Spark. And that was a big problem a year ago. And then they are resolving it, and it's getting better as we go along. As you know, Spark releases on a 3-month cycle, right? So every 3 months there is a new release for that. So, and then they're supporting more. And a lot of good stuff is coming to Spark, including deep learning. Amazing, yeah. So we'll see how it goes. So here I can print the schema. We did that. I'd like to look at the different features that we have here. So for data like this, maybe you should probably do some feature engineering, look at the data and probably, you can probably work out. I mean, I can see weekday, working day in there. Those are important. But then if you have something like a date, which happens a lot. So let's say you have a date like January 20th, 2015, right? You have it in your data. And you look at that column and you see that data all over the place. That's kind of like useless as an information because it's happened in the past and probably isn't going to happen in the future. But then if you break down that column into, let's say, month and day, and then throw away the year, that can turn or give you more information about the season, for instance, right? And then maybe if you look at your problem through a season point of view, then probably you can find that there is a pattern there that can make it seasonal, in which case it has more information per se than just using the plain date as it comes in. So I hope you saw how we can do all those transformations on the data and how easy it is to use data frame API. And that basically not just machine learning, that's also ETL. That's what people do all the time, when they read data in and then they try to, filter it and change it and all that stuff. And then they can move it around and then at the end we can just save it as a Parquet file and then read it back in to do machine learning. Parquet is also good because it's a columnar format, for those who don't know. So if you have something like 1, 2, 3, 4, 5, 6, if you use a row format and then you need just the middle column, then you will have to read all the rows, like all the columns, so that you just grab the middle one. Versus if you save it as a column format, like Parquet or ORC, you will be saving the column first. And then if you, let's say you are interested just in one column, which is very frequent when you're doing machine learning, specific columns, then you can just ask for those, basically. That's what makes Parquet a good choice when you're doing machine learning, besides the fact that it provides the schema as well. Right. So, yes?
One of the steps we did earlier was creating an index.
Yeah.
So when you create an index, is that index an independent object or is it linked to the data frame itself?
Usually when you have like, do you have like a specific example?
No, I'm just trying to correlate the data frame world with
Okay.
the database world that I come from. So
Yeah. So if I have a categorical variable, and then I can uniquely map it to a value, then it will be very easy to go back. That's the idea behind what we're doing here, like string indexer.
right. So usually the purpose of the index is like you don't have to scan the whole table. You have a different object where you go through the index and then you pick up a corresponding value.
Yes.
Right?
Yes.
So in the data frame world, is that concept still the same?
I would say so. Yeah.
So it's an independent object, right?
Yes. Yes. Exactly. Yeah.
And is it also loaded in memory by default or do you have to cache it?
You have to cache it. Yeah. If you want to keep anything in memory around in Spark, you have to cache it. Yeah. Because if you don't, then you'll have to do it again, basically. Yeah. Which could be very expensive. Right. Yeah. So there is that. Now with Spark 2, as I mentioned earlier, we're using Tungsten, and Tungsten is very fast when it's talking to the memory, like SERDs, serializing, deserializing the data. It's very, very fast, wicked fast. So that's good too. The real big problem in Spark that I can see, besides machine learning, I'm talking like in general, is really when you start doing shuffling, and you have to do it because of things like join, So when you're joining data frames and then you're not careful, what do I mean by that? So let me give an example, and I give that example over lunch Let's say you are doing a join, And then your join condition is that, let's say you have one column in one data frame, and then you have another column in the other data frame, and then you are joining on these two columns, right? There are two ways on how you can do that. You can use the triple equal. You do something like df1 join df2, and then the condition will be when column 1 of df1 triple equal column 2 of df2, something like that. This is one way. The other way is I can say, okay, well, maybe I can implement that logic myself. I'm not going to rely on Spark to do it. So how can I do it? I'm going to create a UDF, right? And then my UDF, what it will do, it will take the value from the first column, it will lowercase it, it will take the second value from the second column, it will lowercase it, and then it will do a double equality check, right, inside my UDF, right? So what I do at the end, I do df1 join df2, and then I call my UDF by passing those two strings to it, right? What happened is Spark, when it sees a UDF, it is completely opaque to Spark what's happening in there. It ignores it, basically. And all it sees is just that you're trying to join two things, one called df1, the other called df2, but it doesn't know how you're doing it inside your UDF. So it will trust you on that. And then what happened is, if you run this and you look at the UI to see what happened between the two stages, so you see stage 1, df1, stage 2, df2, and then you see stage 3 when it's trying to do that join. You see that it's called the Cartesian join, which is big O of n squared, which means it's not going to finish, right? Just wait there. Why? Because Spark trusted you in providing that piece of code. So how do you fix it? Well, I will take my UDF, and I will strip away that comparison from inside the UDF. So I'm not going to do the double equal anymore. All my new UDF does is lowercase that string. And then if I change my code to do something like df1.join df2, and the condition will be like my UDF string 1 triple equal my UDF string 2. Now Spark sees the triple equal and understands what you're trying to do. And it's really well optimized for that stuff. And if you look at the UI again, instead of looking and seeing a Cartesian join, you will see a sort merge join, which is an n log n, basically, right? And you gain that n log n from Spark because you used predefined functions in there. Does it make sense? So when you're writing Spark code, first thing is look at what you can use out there. If it doesn't exist, then you have no choice. But I'm sure that usually there are a lot of stuff that have been written for Spark that are in there, yes.
Doing a group by that causes certain data to aggregate on certain nodes. Is there a way to say, well, in general, I want that data to co-locate? Is there a way to ask it to do that? If you're grouping by town, and I want all the data of people in the same town to be on the same node, generally processing them together, is there a way to tell it this is just for this calculation, but in general, this is how it is?
So his question is, if you use group by, and then you want the data to be co-located with another data, is there any way you can do that? Is that what it is? Yeah. So when you use group by, under the hood, group by uses something called the custom, the range partitioner. Basically, it's a partitioner that spans that passes over the data and sees what to do in terms of partitioning and all that stuff. One solution will be to write your own custom partitioner in that case. It's advanced topic, but it's doable. Yeah. Bear in mind that when you read data from the source, Spark tries to mimic what the source does. And then if you, let's say I go back to HDFS as an example, and then because HDFS uses locality embedded within it, because as I mentioned, it tries to keep the data next to each other in the same box, in the same rack. If it can't, it's going to put it out there. Spark tries to use that locality as well, out from the source. So those are the tricks probably that you need to look into. But usually you can go down that route and do the custom partitioner as well. Another thing that I probably should mention, which is not part of machine learning, but it's really an advanced topic, it's about the rules inside the catalyst. Because if you remember, I said you have the query, and then the query will be analyzed, like create logical plans, and then at the end, it will create many physical plans out of that best logical plan, and then that best physical plan gets translated into bytecode, an RDD code at the end. Now, the question is, can I change the catalyst to think like I want it to do? Like I want the catalyst to do my own rule. It is possible. That stuff, it's still experimental at this time. Even the API has the experimental name in there, but it's going to be very stable. And how it works, you would create your own rule. You will subclass a class there, a strategy class. You will create your own rule, and then you will plug it inside the catalyst. And then if the catalyst thinks that your rule is better, then it will be chosen. And how do you know if it was better and if it was chosen? You go again to the UI, and under SQL, you look at the analysis of the logical plan and the physical plan, and you should see the name of your rule in there if it was picked up, basically. Yeah, but those are the things. I mean, you can do a lot of advanced stuff now on Spark, not just as it used to be. Okay, so let me stop here. I think you got an idea here how to do things using the pipeline, because it all boils down to the pipeline, by the way. You know, once you create the pipeline, you call the set stages on it to put all those components that you're interested in, and then you can embed a pipeline inside another pipeline, as we saw here. You know, like the pipeline that does just the machine learning modeling, and the pipeline that does the cross-validation. And then once you call the fit on it, on this cross-validation, then you are presented with the best model, basically. Once you have the best model, as I mentioned earlier, you can either stick it into Spark streaming. If you're using the RDD, you're going to that for each loop. If you're using structured streaming, now you have just a data frame API, you know, that you can just call the model on, basically. So let me stop here, and then we'll continue in probably a few minutes. But I would like to ask you if it's possible for a post-class survey, and that Databricks expects at least like a 90% response rate for those surveys. It does use those to, change and modify the training material out of these classes. So I would appreciate it if you can just take a few minutes and fill up that. Let me show you what it is. So if you go back to your file, it should say here class surveys. So you have done the pre-class survey, and I think it's time to do the post-class survey, this is the link to it. You don't have to provide your name and email if you want. So I'll give you like a few minutes, and then we'll resume. Any questions so far about what we covered so far, like this morning and this afternoon? Spark Core or machine learning? So I hope you see the difference between the RDD API and the data frame API. It's very important, because if you work in the RDD API, the code is not going through the catalyst. So basically, you're not gaining like the goodies that or the optimization that you get from the tungsten, for instance, through the SERDES, as well as the code optimization. Yes? Is it possible to get you the catalyst to give you what? Yeah, yes. Exactly, yeah. So his question was, is it possible to get you have the catalyst give you the data frame or the optimized data frame and then modify it? Is that what it is? I mean, you can always look under the hood just by looking at the physical plan. You gotta know what you're doing. That's the tricky part. Because if you don't know how to read that stuff, it's really hard to make sense out of it. But it's there. For people who know how to read it, it is there. That will show you like, let's see here. Is there interest in looking at a notebook that shows the catalyst under the hood, how it works? It's a quick one. If there is interest, I can do that. Who wants me to go through that? Okay, all right. So let's do this. Let's do that, and then we go back to doing scikit-learn.
Basically, one related question is that how we find out whether the optimization is what we desire. You just mentioned about the opportunity for customizing the kind of the execution plan. But when we know we need to customize it, so it's kind of based on the analysis of the SQL type for the execution plan.
So when do you create your own rule?
Yeah. So
I mean, that's what I said.
understanding under who the execution plan before we try to.
Yes, I mean, that's what I just told him. You need to know how to read that. Yeah, and then once you understand what the catalyst is doing, then you can see that you can improve it. Then yes, you add your own rule to that. So let me see if I can find. Yeah, for some reason I can't find it here, but I'll find it during the break. Once you go on the next break, and then I'll find it and run it. Let's see here, Spark Day. Day 2. Yeah, for some reason I can't find it here. I know I have it somewhere. Yeah, I'll find it during the break and we'll do it. So let's go through scikit-learn. So in here, again, the idea is very simple. You are so good at creating models using scikit-learn, but you want to take advantage of Spark to parallelize that job. That's the idea. So we know that scikit-learn is really great at creating models on one machine. But when it comes to cross-validation, we want to take advantage of the environment to do that in parallel. So that's the idea here. So we first start with part one, where basically we're just using scikit-learn to do some stuff, probably some easy stuff in here. You know, we can look at the data, and as you can see, you can just run scikit-learn or Python as you would on one machine. For instance, I personally do research in Python, right? And then what I do, I create an egg file, and then I just import it into this environment, and I can just call it from there. You can also do this kind of stuff. And let me show you how easy it is before we move on here, how easy it is. Who's familiar on how to load third-party libraries on Spark or in the Databricks environment? Okay, so it's very easy, actually. The way you do, if you click on Workspace, and then you go, like, let's say, under here, or it could be under your username. If you click here, and then you say Create, you hover over Create, it shows you create what? A notebook, a library, or a folder, right? So if you go under Library, then you have a choice. You can either do, I want Maven coordinate, in which case you are bringing in a jar file, right? And then if you select Maven coordinate in here, and then you just give it the name here of the library that you want to bring, and then you say create library, it's going to go and get that jar file and get all the dependencies along with it, basically, and then install the library for you. Things like, for instance, you want to use graph frame, right? You would do that. Because Spark does not ship with all the connectors. Like, for instance, if you're doing Spark streaming, you would need Kafka. If you're using Kafka, you would need Kinesis if you're using Kinesis from AWS. Then what you'll do is you get those libraries, and then this platform will install them for you. This is like using the UI. If you had to do it your own, it's kind of involved, because if you had like your own Spark installed somewhere on-prem, then you'll have to go to the conf directory and open that default environment file, and then you'll have to do that yourself there, add in all the connectors, like through the -- packages keyword in there. But if you use this environment, it's basically just point and click. Now, you can bring in a Maven coordinate, or you can also bring in like a PyPy, right? You can also bring in a PyPy in here. Okay. So let's go back to scikit-learn. So we look at some of the data here. Same thing for R, by the way. So Spark R, because the reason I'm kind of like keep talking about this stuff, because I looked at the questions through that pre-class survey. So I noticed there are a few questions that I'm trying to answer as we go. Spark R is gaining support in Spark, right? So when it started, it was really just data frame manipulation, right? For those familiar with R, basically all you could do is just manipulate. And then as we go, machine learning algorithms on R are being added to Spark. So after this one, I'll show you the source tree of how Spark is laid out on GitHub, and then where things are for Spark R, for Python, and for Scala. And basically, if you want to take a look at the code and see how it works. So let's keep going here. So here we're building a nearest neighbor classifier. Not that complicated. A KNN, right? So basically, let's say a 3K equals 3. We look at the 3 neighbors, and then we make a vote, if it's a classification or regression, right? An average. So classification, we make a vote, and then that's the KNN, basically. And we were doing that through scikit-learn here. Then we define the grid search. That returns an accuracy. Because remember now, we're creating code that we will be shipping to the nodes, basically to run on the different parts of the data, right? And then we can parallelize some data. By the way, SC parallelize, for those who don't know, returns an RDD. So basically, this is a way of how you can distribute in parallel the data over the different nodes, right? And usually, this is like a really good way of testing stuff. So if you can just create like some fake data, or even if your data sample is small enough, you can use SC parallelize, kind of like to ship it to all the nodes, right? Now in here, we're using this broadcast variable. So for those who are not familiar with broadcast is a very powerful concept. So let's see, I'll go back to that joining two data frame problem. So if you want to join two data frame, and joining involves shuffling, and shuffling involves complexity. If one of your data frames is small enough, this is a threshold that you can set in the Spark configuration. You can say like anything less than, let's say, 10 meg is small. Then what Spark will do, it will ship the data to all the nodes. And then instead of joining through a shuffle, you will be basically, a copy will be a local on each node, and then the join will be local type of thing, right? So this is very helpful when one data frame is not big enough versus you have one small, one big. And then, what is it? Yeah, because you don't have that every time. Basically, the case where you have one small, one large. Because if you have like usually big data frames, then you have no choice. But then if you have that case most of the time, yes, I agree with you. Broadcasting can save you a lot. Sorry? When you have a small data set and you broadcast it, it will be shuffled, right? Okay. And then what was the question?
I was asking why not do this every time when the data set is big or small?
Yeah, because if it's a huge data set, you can't make it fit on a node if you broadcast it. So you are limited by the memory of the node itself, right? So because when you broadcast, don't forget that you are shuffling, but the price you pay for broadcasting, you will gain from it later. You will incur a penalty in shuffling the data, but at the end, joining later will be a lot easier and a lot more performant if you broadcast the variable, basically. Okay, so here we broadcast. And then now we can do cross-validation on it, where basically the cross-validation is running. We're doing a k-fold cross-validation. It's running on each node separately. So each node now is trying to do a cross-validation on its own data. That's the whole idea here, right? I'm sure that people who are familiar with scikit-learn will find this kind of like a very easy example to do. But the idea, again, is not to do machine learning as it is just how to use the tools on Spark. Right. Any questions? Yeah, so you should probably think about this kind of stuff where it is easy to parallelize things like CV, and there are other things that you cannot parallelize easily, unfortunately, then it's harder to achieve in a parallel environment. So there are stuff that's not embarrassingly parallel, then that could be problematic. Yeah. Okay, so let's stop here for the break. And I'm going to look for that notebook to show you what's happening under the hood in the catalyst and how we can, even though the code is kind of like a dumb rule that we will create, but because it is dumb, we will force the catalyst to choose it. That's the idea. And then we can look at, see that it picked it up, basically. So let's stop now for like 30 minutes break. So let's say we are in this situation where we are creating table A and table B, just dumb values, 50 million of them as A and as B. Let me just attach part 2. And then I do display results. And what I'm trying to do here is join, as you can see. So I'm joining A with B, given this condition, that A of ID is equal A of B of ID, right? And then I do group by and account. And when I do that, you can see it's taken some time. Let's see how long it takes. You see this 200 here? This is what I was talking about. Like if you are in your own environment, that's the one you should tune, given the number of nodes and all that information. But you don't have to, actually. But all right, so it took like 36.20 seconds, right, to basically join those two data frames together. So even though the example here, it's not that important, right? But what we're trying to do is, what if we have an array, and then we are joining it with another array that overlaps with it, right? So if, let's say, we have a situation, which is in this case here, when we have one array, and the second array is inside that first array. So how do we join in that case? It would be just to reassign the starting position and the ending position, because in this dumb example, it's continuous values, right? So the idea here is not to improve the join, but to come up with the rule that we are sure it will be picked up by the catalyst. That's the idea. So if we look at if we do the result explain true, it will give us this as a result. Basically, the parsed logical plan, the analyzed logical plan, and then finally the physical plan. And then we can see here that, let's see, we are doing a sort merge join, right? So when we're doing the sort merge join, sorting and merging is expensive, right? Because shuffle will be involved as well with this. So let's see what we can do. So this is how you would write your own rule, basically. So we'll call it interval join, and then you will extend the strategy, and you'll have to make it serializable. So basically, that's the protocol and how you change or how you add a rule there. So in our rule, we're looking for the case join. And what we're doing is we're looking for, I mean, I'm not going to go through every line of code here, but basically, I'm looking for making sure that start 1 is less than end 2, and then end 1 is greater than end 2. And I'm creating this new start and this new end. And I really don't care about this because this is the partitioning, how many partitions I need to use. I don't care about that. But what I care about is really to create a new range that starts at start and ends at end, ends at end, right? This is basically the idea. And then if I can do it, then on Spark usually return a nil, right? So let's say we create this rule, and then we're hoping that this is so simple that the catalyst will pick it up. So how do we do it? So we create the rule, And then this is how we plug it in there. Spark.experimental.extra strategies equal our new rule, interval join. This is how currently we add stuff. It's still in experimental phase. And then let's run again. So when we ran this display before, it took what? It took 36.20 seconds. Now let's run it again, and it should be fast. And it takes 0.30 seconds, right? Not even 1/3 of a second. If we look at what happened, we see that our new catalyst picked up the range instead of the sort merge. Does it make sense? Yes. Yes. Yeah. Yes. In this case, again, it's kind of like a dumb example. But the idea is not to improve sort merge. The idea is to make it so easy that we are sure that the catalyst will pick up our rule instead of using sort merge to do that. Now, in your case, you'll have to, I mean, that's not an easy stuff, but it's doable. You know, you can analyze what the code is doing, and then if you see that it needs improvement, then you can improve on it and then create your own rule. But the idea here is just to show you how you can add your own rule and force the catalyst to pick it up. Because the catalyst really works on a cost object, a cost algorithm. So once it creates all those logical plans and then the physical plans, you will have to compute a cost for each one of them, and then the lowest will be selected. In this case, it will be this range here. Is it clear? Yes? That's a good question. I don't have an answer to it, but I can get you. I mean, this is still pretty new stuff. Right? I would say that probably at this time, probably just one, but I'm just guessing here. No, but I can give it to you. That's for sure, no problem. Yeah. There's also a question in the Q&A that asks about the PDF for the slides. So I'm going to also put that under your student folder. So if you go to that reference document, you have that, if you go here, under this file that we saw earlier, and then if you scroll down to file sharing, there is this link here. If you click on it, it will take you to where the DBC is, the one we use today, the labs, and then there is the Q&A parking lot file. So I will put the PDF file of the slides I showed you this morning. I cannot give you PowerPoint presentation, PPT, but I can save them as PDF and put them in here. So you will have that PDF. You will have the notebook I just showed you. And there's another one, if you're interested, that shows the big O and square and how to turn that into n log n. If you're interested, I can show you that as well. And I can give you that as well. Okay? So let's do that. All right, so for that to work, I will need Spark 1.6, which I just created a cluster, just in case. And so I just called it like clickstream DAG. Okay, I'm going to do this. And while it's running, I want to tell you something about this notebook. It was created by a guy called Andrew Orr. He used to work for Databricks. Now he's at Princeton. He has a video which I find interesting to watch. He talks about how to use the UI, how to debug Spark. So I will also add a link to that video for you to check it out. Right. So what I'm trying to do here is this. Because we haven't used the Wikipedia, usually that's the data source we use, especially for Wikipedia classes, is we have this case where basically in Wikipedia, when you're looking at an article, you have incoming clicks and then outgoing clicks, right? So people coming in like from Google or Facebook or Twitter into Wikipedia, and then they read the article, and then they will click on a link, an internal link, to either stay within Wikipedia or leave. So what we're gonna do here, I'm gonna show you how things work for this problem, is we will measure how many clicks are incoming, and then how many clicks are outgoing. And then we will create 2 data frames based on that information. So incoming clicks, data frame, outgoing clicks, data frame. And then we'll join the 2 together. And then we'll try to create a new column in the result data frame, which will hold the ratio of the incoming to the outgoing, right? And then that's the idea. So again, the idea is not to do something fancy, but to show you what we can get stuck easily if you were not careful when we're doing joins. All right, so let's do that. So here's the code. What I'm doing in this code is this. I'm creating this in-clicks df, right, as I said. So I'm grouping by this current title, and I do a dot sum. So let me tell you something about this as well. Group by returns a group data structure. It doesn't return a data frame, right? In order to get group by returns a data frame, then you'll have to call functions that are within the group data. Among them, sum is one of them. So by calling sum, basically you are getting back a data frame from that group by. Does it make sense? Okay, so after sum, now we have this new data frame, and our data frame, we are renaming the column sum of n. Again, when you call sum and you don't specify which column, it's gonna go over all the columns that it can sum, right, which are numerical, and then it's gonna sum them for you, which is kind of like not a good idea if you have 100 columns and only one is numerical, right? So what you would do in this case, you would provide the name of the column that you want to sum. But if you don't provide the name, it's going to sum everything that can be summed, basically. That's what I'm saying. So then we select the current title, and then we select 2 columns, the current title and then the in clicks, right, as in. Then we do the same thing for out clicks data frame. And then we create this UDF that we don't like. In our UDF, we are taking string 1 and string 2, and then we are lowercasing the first one, and we are double equaling with string the second one. And then in the third step, what we're doing, we are doing join df, which is the result that we're hoping for, is the out click df, join it with the in click df, given this compare condition, which in this case will be the call to the UDF, compare, and pass into it the in current title and the out previous title. So we're hoping to compare those 2 titles, and if they are the same, then we join on that condition. That's the idea. And if we are successful, then we would like to create a new column on that new data frame, and we want to call it multiplication underscore factor. And the value of that will be out clicks divided by in clicks. That's the idea. And finally, we select a few columns in there, including what was in there, plus this new multiplication factor column that we just created. That's the idea. And then finally, we use display to display the results. So I have started this since I started talking. And then if I expand this, you should see it hasn't even started 0 out of 40,000. Right? And it's not going to finish. It's just going to sit there because it's a Cartesian joint. This big O of n squared. And how can I see that? If I click on view, I will see that I have stage 4 and 5. And then in 6, I'm trying to join. So if you look at the stage 1 and stage 2, they have these arrows here. Those are called the tungsten exchange. Those are the shuffled data. And then they go, both of them, as an input to the 3rd stage, in this case, stage 6. And then here, I'm trying to join them together, and the join is a Cartesian product, as you can see. So it's just going to sit there forever. It's not going to finish. Why? Because Spark trusts you on what you're doing inside that compare. And it doesn't even try to do anything. Because Spark will look and see compare in the step number 3, and then everything within that compare will be completely opaque. Right? Spark won't see anything in there. So how can we fix the problem? First, we need to cancel the job, because we can do it. If I can even cancel it. Close. Oh, did I lose connection? Reload page. So let's cancel that. Yes, I want to cancel it. Okay. So here's what I do. Here's how I would change things. First, let's recall the new UDF format, right? So we rename it format. And all it does, it just takes in a string and lowercase it. No more double equal in there. And then inside my join, I do join as before with in-click df, but this time I'm doing format on current title, and I'm using the triple equal now on the columns. And then I do format previous title. And as before, I create this new column, and I select few columns in there, and I try to display. So let's try to run this one here. But now the difference is that Spark sees the triple equal and understands what you're trying to do. As before, it couldn't. And hopefully I'm not going to get embarrassed here. And it's going to finish in time. At least we don't see 40,000 anymore, like we did before, right? So this is definitely is going to work. How long is it going to take? No idea. We have that 200 in there, which is kind of like bad. If we could have also changed the 200 to be like 16, because our environment has 8 threads. So if we do 16, it means like it's gonna execute the first 8, the second 8, and it keeps on. Here it's done now, right? So if we look at the UI as we did before, same thing, stage 7, stage 8, both of them feed the third stage, actually more stages that got created. But here, the final stage where the merge happens has been changed to sort merge join instead of Cartesian join, because of that one change in the code. So what we should take from this is that if you can use whatever it's predefined in Spark, use it. Don't rely on creating your own, because you may very easily create situations like these, big O and squared. Any questions? Okay, and I'm gonna add this to your folder as well. All right, so let's go back to machine learning, last part. Let me just kill this one here. Okay. So if I go back to me, K-means unsupervised. So what's the difference between supervised and unsupervised is really why. We don't have the output, right? And in other words, probably plain English, we're shooting in the dark, right? It's really hard to create a model for unsupervised, but if you are successful, it could be a very good model because it would not overfit, right? Because it doesn't depend on why. So creating the model is hard, and that's where probably things like SME knowledge, like subject matter experts, helps. You know, You try to create, especially things like k-means, when we have data that's not colored, and then we're trying to put a color on it, kind of like cluster it into a bunch of clusters. What we're missing is really the number of clusters, right? So we can start randomly, and then we test the data, look at the data, or try to understand it through some subject matter experts. We can also do tricks like maybe use LDA as a topic modeler, because when you use LDA, which is the latent Dirichlet allocation, what you're doing is you're looking for a matrix of weights that relates documents to words. And then basically you're looking for those hidden number of topics that are in between the documents and the words. And then if you're successful and you give me a document, I can tell you like, okay, this document is 50% entertainment, 25% politics, and 25% food, right? If you are successful in creating those topics, that could be like a good starting point, kind of like to think about the number of clusters to use, maybe. So LDA in that case can be used like as a predecessor to k-means. K-means, the way it works, and I'm sure you know, you start with the random centers, right? And then through an iterative process, you start refining those centers as you go. So each iteration, you are kind of like remapping the data through a measure, something like Euclidean distance, right? And then until you start, it converges, and then probably you call it done. Other people, they thought, like, how can we improve this instead of just randomly looking for or picking those centroids? And a technique was created kind of like to use some kind of like probability guessing into how can we pick those centroids in a better way. And that's k-mean plus, right? And then when k-mean plus came out and people just start using it, they said, okay, well, can we parallelize k-mean plus? And the answer is yes. So, and k-mean parallel came out, which basically was started from k-mean plus. So Spark, by default, uses k-means parallel, by default. Unless you want to change it to use k-means, the old one, then you can still do that. But if you don't do anything, then k-means parallel, which is under the hood, is really k-means plus, is used for you. So in this notebook, what we'll try to do, we have a data set of, let's see, 20 news groups data set. And then we'll try to see if we can use k-means and how we can do that, which is the first time we're looking at how we can use unsupervised on Spark. How we can do that to try to cluster the data together, right? And in this case, as you can see, it's the same thing as before. It is not a long one. I don't know if you guys are tired, but I think you should probably just run through it, on your own and see if it at least makes sense to you. Basically, you cluster the data into those clusters, and then let's see how many clusters we're using here. Okay, so we're kind of like cheating. We're using 20, right? You don't. That's the $1 million question.
So is there a way you can show us how to use the LDA to...
Well, not today. No. It is an involved one. No. What I suggested is maybe if you just use the LDA, kind of like to guess. This is still not obvious by itself, but at least it can give you an idea. If you're looking at the topics, and then if that makes sense to you, then that could be a good starting point. In this case, we are kind of like cheating because we're using 20 as a starting point for the number of our clusters, right? But that usually is not the case. So in this case here, we have this data set of news group, and then we'll try to see if it makes sense after we run this notebook, if we are able to create 20 clusters, and if those documents, which we can tell from the title, make sense, the fact that they are clustered together or not. So that's the idea behind k-means here. So why don't you maybe spend like 10, 15 minutes on it, and then we can talk. Something that I need to mention here is TF-IDF. So who's familiar with TF-IDF? Okay. So we haven't seen so far TF-IDF used on Spark. And Spark supports it. So TF, which is called hash TF, is a transformer, right? Because all it does, it takes a data frame and basically counts the number of frequencies for those terms. So that's a transformer. What we're trying to do through TF-IDF, kind of like in plain English, is we can like say, okay, we have a bunch of documents. If a word happens a lot, doesn't it make sense that probably that word is important? Then yes. Then so can we just compute the frequencies of those words and see if they make sense? Maybe they are important. But then by doing so, we're creating another problem. Like those stop word words, they happen all the time. Like or the or from, you know. They don't have no information to add. So we're trying to get rid of them. And that's what we do through IDF. Right? So we can like to reduce the impact of those words. So TF is implemented and it's called hash TF in Spark. And it's a transformer. IDF is an estimator. So it has a fit function because it's more complex to do IDF. And then you just call them basically to get to create those components as we did before. And as you can see here, hashing TF has a transform and IDF has a fit function. We will be doing normalizing as well. We will be normalizing the data. And then at the end, we just create the k-means using the seed and the set k of 20, which is, as I said, is kind of like cheating in this case, but we'll see how it goes. All right, so let's spend some time on it. There is this evaluate clustering, maybe going back to my friend's question there. How can we come up with the number of clusters, which is kind of like hard? There is this compute cost. It doesn't mean anything by itself, but then if you compare it to some other k-means models that were created, maybe it can give you some hint. But just looking at the value and then kind of like guessing what it does, kind of like hard, right? So let's spend some time on this and then we'll talk again. Maybe you have noticed today, when we used NLP, we didn't use any of the n-grams. Like no bigram, no nothing. Right? We just kept it simple. No stemming, no n-gram, no nothing. But I'm sure if you use that stuff, obviously it's going to improve the quality of the model itself. But we just don't have time to do that. All right, so let's go through this quickly here. So what we're doing here is, as before, we're using a tokenizer. We saw this minimum length of 4. We're setting the input and the output column. And then we're calling transform on it because it's a transformer. And then we do the stop words remover, again, tokens and filtered. And then we call the transformer on it. And then we call the string indexer, and we saw that, right, as before. So this is what we got. And as you can see, we keep building on the number of columns, text, label, tokens, and filtered. And then we use TF-IDF. We call hashing TF by setting the input and the output columns. And then we set the number of features to 20,000. Usually when you have a document and then you compute the most important words out of that document, you still end up with a huge number. And probably you don't need that, so you just need the top important one, usually 20,000, 10,000. I've seen all sorts of numbers there, right? And then you do IDF, and you call transform, because it's a transformer, the last one, the IDF model, because again, if you remember, IDF model is returned from the estimator, which is IDF in this case. So once we have the IDF model, which is a transformer, then we pass in that featurized data DF, and then we drop a few columns from there that we don't need anymore. We normalize, and we know why. And we do that after that. We call a transform on it because normalizer is itself a transformer. And then finally, we call k-means. And we set the number of clusters to 20 because we cheated. In a real case scenario, that's not obvious, right? That's the tough part anyway. And then we set the seed, we set the features, and then finally we call the fit on the k-means because it's an estimator. And once we do that, we come back with this model compute cost, because it's there, we can use. Does it mean anything? Looking at the value like that, it doesn't mean anything. So you'll have to compare it to something else. Right? But it's there if you want to use it. And then finally, we can even print the clusters, the centers, which look weird and ugly display, but they're there if you want to look at the centroids as well after that. And then we look at some of the data. You know, we can print, like if we print based on the prediction, we group by prediction, we can right away see that group number 2, it's kind of like a catch-all cluster, right? Basically, maybe it's kind of like weird-looking cluster there. But we can also see that 13 has some information, 6 has some information, 5 has some information in there, right? So what can we do? We can pick the cluster. In this case, we pick cluster number 1, and then we group by the label, and then we can see it has only 2 elements in there, motorcycle and science electronics. I don't even know it makes sense or not, but that's what it is. We do 6, we group by label, and then we can see that it has a bunch of stuff, like the second one, rec sport hockey, which has a count of 24. Now, can we reverse that now? We know that hockey appears 24 times into that cluster, which was number 6. Now, can we reverse that? Like, can we look for rec sport hockey and then group by the predictions? We want to see where this thing happens in which clusters. And if we do that, we can see that it happens in cluster 6. So that's, I don't know if that's good indication maybe, but at least you have some insight here. You can go back both ways. You can go this way to go to the cluster and then go backward to see if those really are there as they claim. That type of information that you can do with k-means. And at the very end, there's this probably bonus exercise that for sure you're not going to do it now. But it's a good one. Maybe if you can convert this code, because you'll have access to it, convert it to use pipelines instead of just write it the way we did. So if you can just turn it into using pipelines, as we learned today, and then you just call the fit on the pipeline, and the pipeline should take care of everything for you, running all those different components inside as a pre-process step, including TF-IDF, and then finally computes the k-means for you and give you back a model that's unsupervised, basically. Unfortunately, we didn't cover a lot of unsupervised today, but I just thought, like, if you understand how you do it for k-means, it's going to be very easy to do it for any other unsupervised case, right? You can, for instance, use it for PCA. PCA exists. You can just call it on a data, you just call PCA, and then you'll get back the PCA values. PCA, basically, in a nutshell, what it is, if you are in a very high dimensional space and you're trying to kind of like linearly connect all those columns, and usually if you move to that PCA space, you will capture most of the directions and most of the energy in the signal through just a few PCA elements or coefficients in there. And then once you do that, then you will reduce your space from high-dimensional space to a low-dimensional space. And then after that, you can do things like linear regression and things like that. This, by analogy in the digital signal processing, will be something like Fourier transform, right? If you are in the space like time, space, or speech, or video, or image, and that working in that space is very complicated because it's mathematically it's a convolution operation. Then if you move to the frequency domain through Fourier, then you end up with just a few elements that captures most of the energy in the original signal. Then a convolution turns into a dot product in the frequency domain. This is very similar here in terms of PCA. If you have a lot of columns, very high dimensional space that you cannot do on Spark because you have a lot of columns. Another option, if you're looking for PCA, is to get it through SVD. So SVD is supported on Spark. It is just RDD based, though. There is no support for data frames for SVD. But the idea is if you have a matrix that you can decompose into those famous three matrices, namely U times sigma times V transpose, the PCA will be U times sigma, basically. So if you compute the SVD, then you can grab the PCA out of that as a workaround, if you can do it directly through PCA. So there are a lot of functionality that exists right now on Spark. And as a matter of fact, I wanted to show you how the code looks like, just to get an idea. So if we go to, actually before I do that, before I forget, I have these two slides that I need to run by you guys. There is Women in Big Data lunch, which is Wednesday, February 8th, between 12:30 and 2:30. And not just women are welcome, even men. I was told to say that. I mean, maybe the title is misleading or something. So everyone is welcome to come. You want me to make it bigger? Larger? Okay, sure. Ooh, wow, look at that. Oh, that's worse. Oh, for Google, you have to go the other way around? Oh, what am I doing? I'm hitting minus now, and it's zooming. I don't understand what it is, but it works. So welcome remarks and Women in Big Data updates, 12:30 to 12:40. And there's a keynote and a panel discussion from 1:30 to 2:15, and networking from 2:15 to 2:30. And that's happening on Wednesday, February 8th. The second one is tonight, and that's the Pre-Spark Summit East meetup. And it's happening today between 6 and 9 p.m. if you want to connect and talk about Spark. So let me show you where Spark sits. So if you go to Spark, take that back, GitHub, and then search for Spark. So this is the code base for Spark. And as you can see, let me make this. How is it? Does it look good back there? Huh? Pre-built version? Spark with Hadoop? No, okay. Yeah. So basically, this is the code base for it. And okay. And we have the R folder in there. So anything R goes in there, basically, to create wrappers around the code that's written in this column for the R, for Spark R. There is, same thing goes for Python in here. This folder in here for Python. You have this MLlib local and MLlib. So MLlib local, they were just recently working on it. Recently, probably a few months. Maybe it's there by now, I don't know. But basically, they're creating an environment so that you can run the Spark locally, and then you don't need to import any of those algebra libraries and all that stuff. So everything will be there for you to just use as a local version. And there's this mllib folder, which we will go into, and there's source, main, and then this thing here. Here we have two folders, ml and mllib. So mllib is the original one. That's where everything is, right? So if I go under mllib, I can see that I have classification. This is what I can do. Logistic regression, naive Bayes, support vector machine. And I have clustering, right? This is what I can do so far in clustering. LDA is mentioned in there. And then there is this library here. And there's feature. Actually, there's eval, which we saw some of it today, right? Binary classification, multi-class matrix, and all that stuff. And there's this feature folder, which has a lot of stuff in there. Oh, actually, you can do chi-square selector. Chi-square basically helps you reduce number of features that you have. You can do hash NTF. We saw that. IDF is in there. PCA is in there, right? Word2vec. And obviously, you can go in there and look at the code as well, right? And there is this optimization folder in here. So what they do, every time they can take a code that they can optimize or like accelerate through some tricks, they will put that in here. And this one will be used, basically, when Spark is running. So that's the idea behind it. Not everything that you see implemented on Spark will make it here. But if they change it, if they optimize it, then they'll push it to this folder in here. And they have recommendation. They have ALS, which is a great topic. ALS is actually one of the maybe two algorithms that don't need the driver in the implementation-wise. They are truly parallelized, right? So in ALS, basically, which is alternating least square, when you are faced with situations like Netflix, like things like when you have users versus movies, you know, and then that matrix is kind of like very sparsy, a lot of missing things. So what do? You try to find those low-rank matrices, right? This is really kind of like a completion problem, a matrix completion problem. This is like Netflix, but it's seen differently. So what do? You actually, let me show you. I have one here. Which I just did recently. Gee, isn't this? This was a MOOC project course, right? And then it was kind of like downsized to this notebook here. And basically, what you're doing in this case, you're trying to create a recommender engine. Like if you give it your taste of movies and see if you can predict the same taste or things like that. So this is the math that we're trying to solve behind it. So this is what we're trying to do here, to solve. And basically, if you have a big matrix, in this case is users versus movies, you're trying to decompose this problem into two sub-problems, right? And looking for low-rank matrices for users, low-rank matrices for movies. So what are those low-rank matrices? Low-rank matrices is, let's say you have a matrix which has like 1, 2, 3, 4, 5, and then 1 is needed, 2 is needed, but 3 you can derive it from either 1 or 2. 4 you can derive it from 1, 2. Then in this case, instead of having a rank of 5, you end up with a rank of 2. Right? That's the idea behind that. So, and because they are both changing at the same time, then we need to fix one, and then work on one, and then fix the other one, and work on the other one. So we fix users, we work with movies, we fix movies, we work with users. Because of the fact that we're doing that, now we are alternating. That's why it's called ALS, alternating least square, right? But basically, we're trying to minimize this function here, which is least square error, and then we have that lambda w in there, which is kind of like norm 2, which is basically a regulation parameter in there. So we have that one in there. What I wanted to tell you also about, so we have, okay. So if I go back here, this is ALS, and then you have I don't know if random forest is here. Yeah, you have, no, not this one here. And the random forest is somewhere here, and the regression, I think. Yeah, we have ridge, regression, linear regression, lasso. So let me take a look here. Yeah, so we have decision tree, which we use today. There is gradient boosted trees, which is an ensemble technique, which we use today. And there is random forest in there too. I think I saw a question on the Q&A, but it was answered before I answered it. So it's very easy to use random forest instead of just GBT. So that's why I keep telling you that they did a great job in maintaining the same API. To allow people to kind of like switch between supervised and unsupervised, different algorithms in supervised and so forth. So this is MLlib. And if we go back to ML, it's the same thing. And this is where the new stuff sits, based on the data frames, not RDDs. And the idea is to keep moving things from MLlib to ML. And when that happens completely, then MLlib will be completely phased out. And they're talking about Spark 3.0. In that 3.0, it will be completely deprecated and would probably even not have access to it. And in here, again, we have the same thing. We have clustering, and this is what you can do. And obviously, you have this big one, which I think feature, if I'm not mistaken, feature, which basically allows you to do a lot of stuff. We saw the binarizer today. We haven't used the bucketizer, but it's there. You can take a look at it. Count vectorizer, we used it. Chi-square, we didn't, but you know what it is. Hashing TF, we did IDF, and a bunch of them in there as well. PCA is in there as well. Any idea? Any question? All right, so let's say you created a model. Now, how can you have you heard about PMML? Predictive modeling markup language? So basically, maybe I should give you those two websites. So let's see. So there is OpenScoring.io. So OpenScoring.io, they are the guys behind PMML, right? So and then if you go to the website, you can learn more about it, like why PMML and things like that. And then basically, if you are in a big data, machine learning, Spark, whatever, you create your model, you can transform it into PMML, and then you can even try it into different platforms. So I encourage you to look at this website and see how to use it, basically, once you create those models. Yes?
Spark support for PFA as well, or just PFA?
I'm not sure about that. Yeah.
Spark exports the models, right?
It does.
What is the difference between the export and the PMML?
Well, I mean, you can export it to S3, for instance. It's not a standard way. I mean, PMML is more like they're trying to make it standard. It's really like XML type of thing, right? That's the idea behind it. There's another one. I think it's called prediction IO, if I'm not mistaken. That's now, it's an Apache, yeah, it's incubating, right? So now it's incubating as an Apache project, prediction IO. This was created by Salesforce, and then they opened it up to open source, right? So this is also a good read, and probably you should visit the website and learn more about how you can use this, which will allow you to run your models in different environments. Okay. Let's see. So we covered, I guess, most of the questions I had. Unless you have questions for me.
Back to the PML and IO, so does Spark support kind of exporting to their format?
I'm sorry, I couldn't hear you.
So I'm talking about, it looks like the PML and the predict IO to standardize the representation of models.
Yes, that's exactly what it is.
How about the support on the Spark side?
Yeah, there is support. Actually, prediction IO supports only Spark at this time.
Oh, that's
Yeah. They only support Spark, and they were talking about supporting more than that. Yes. So that's why if you go to their website and can like learn more about what they're doing, you'll see what they're doing. Yeah. Okay. Let's see here. So I think I saw this, and this is how you would call train a random forest classifier. Right. Yes, sorry.
I think students should have access to that as well. That's great.
Okay.
Thank you.
Yep. No, broadcast does involve shuffle. But on the long run, you're better off using broadcast than shuffling the data when you do a join, right? Especially if you end up in a situation where you have like skewed data frame. That's really bad, right? But if you have like, let's say you have like, you end up with the partitioning scheme where you have most of the data on one partition, some of the data on some other partition, probably nothing on some of other partitions. This is a really bad situation because in this case, nodes that have no data are not doing anything, right? This could be problematic. So in which case, then you have to kind of like repartition the data. It's tricky repartitioning the data, but it involves understanding your data, you know, on how you can remap it, type of thing. Now it's a lot easier with the data frame to work with Spark. It's so obvious and straightforward compared to how it used to be with the RDD and the map and the reduce and all that stuff, because you were really in charge of creating all that lower level code. You still can do that if you need to, but try to stay away from it. Now, if you are in Python, maybe, I don't know if you guys are Python users. Let's say you are in Python, and let's say you don't find what you're looking for to do through the data frame API. And then you decide to create your own map or your own reduce, so which means you have to drop down to the RDD. In that case, if you write it in Python, then you will incur the penalty we talked about this morning, right? If you remember that blue graph. Coming from Scala will be a lot faster than doing Python. So what do you do in that case? There is a workaround that a colleague and friend of mine, he was in the room earlier, he created, and he's going to open source it, in which case then the idea is try not to write it in Python. Write it in Hive. Because if you can write it in Hive, then you will still be within the JVM. And the JVM will understand how to do it, because Hive under the hood is really Java, right? You're doing MapReduce in Hive. So when you issue that HQL statements in Hive, they get translated into Java MapReduce under the hood. And if you do it that way, then it will still be in the JVM, and then you will not incur that penalty going back and forth between the JVM and Python. So there are tricks like that that you can also do, waiting for better solutions. So let me move and come back to that. Why are shuffle partitions? Who's typing? Are you typing? Okay. Why are our shuffle partitions defined as a fixed number, 200, and not a function of the data set and resources available? It is what it is. It is defined as 200, and it is changing. So let's put it this way. It has been found that 200 is a good number for a real cluster. For us, it's a killer. We can do it. I mean, I have another notebook that I ran recently through Spark streaming, structure streaming. And then you can see the impact of the 200, really. You can see it when you're doing structure streaming. Why? Because when you're doing structure streaming, you're doing checkpointing. For those who don't know, if you in any application that does streaming like Kafka or Kinesis, what you do every once in a while, you go and you save where you are in the stream, and you save it in somewhere on disk, right? Kafka saves it, I guess, in HDFS. Kinesis saves it in DynamoDB, because it's a very fast NoSQL database. And then if you lose track, you just go back to where those checkpoints, that checkpoint information is, and you just resume where you left off. Structured streaming allows that now, those checkpointings. To really, the reason is to guarantee write once to the sink, to like the stream data, makes it only once. You avoid doing the duplicates, things like that. So there's checkpointing in there and all that stuff. If you are using the 200, and then every time you're going to S3 to checkpoint, because that's where structured streaming on this, that's how it works. It goes right to a bucket. It's very long. It takes a long time. You can see that. Now, if you change this 200, which you can, it's a configuration value, you change it to, let's say, 8 instead of 200, because we have 8 threads that are running. The speed goes like this. So that's where you see the impact of the 200 when you have things like checkpointing, when you are right into a disk. That value is going to change in the future, but even if it doesn't, then you're in control. You can set it to any value you want through that configuration. Spark SQL shuffle partitions. Thank you. That's the exact name for the variable. That's the one you need to change. Okay. The instructor mentioned Parquet. The instructor would be me, I guess, right? Mentioned Parquet is 25% faster than ORC when encryption is involved all the time. Could you provide more details? Okay, well, that's something that has been done by NASDAQ and made public. And it exists on AWS website. So if you go to AWS website, under use cases and look for NASDAQ, they have a video in there when they talk about how Parquet was benchmarked. And because NASDAQ is highly regulated company, then they need to encrypt at all the time, in transit, at rest, and all that stuff. And because of that, they found that Parquet was 25% faster than ORC, but I'll take this with a grain of salt. Actually, they claim 25%, so I believe them, right? And they did that when they tried Redshift as a solution. So basically, they were moving data from on-prem to Redshift, the data warehouse in the cloud. And every time they were decoding those keys too, right? So this is how it worked. They were so happy with that setup that they built on top of it to create the data lake. Like instead of moving directly to Redshift, then they moved the data to a data lake, and then they controlled the whole process after that. I don't have information about 11.5.12, unfortunately, but I can follow up on that with the folks at Databricks on the progress of that. Oh, TD actually just answered that too. Okay, so you have the answer. TD is the guy behind Spark Streaming, so he knows a lot of stuff. Let's see here. Yeah. Who added this question? Yeah, that's true. Yeah, I think I noticed that too. String indexer is mentioned in there, but it's not used. I think what happened is, this notebook was updated, and that cell was left in there. Yeah, so we need to update that part. This is you? Okay. With RDD, we could have KV data that would suggest partitioning of the data. All similar keys would end up on the same worker.
You can't have a custom partitioner with data. You can only have a custom partitioner.
With RDDs, yeah.
You're stuck with back partitioning. It'll put all the stuff for the same key on the same node, but you can't say what other keys will be on that.
Yeah.
Depends on what the operation is. If you do a join, then it'll do it based on the join keys. If you do a group by, it'll be the group by keys.
Right.
There's no need to. But it won't.
What we missed today, actually, let me just go back to your content. By the way, you have a month for this stuff. That you need to grab this stuff from here within a month. What you can do, I'll show you how to do that. If you just go here, and then you do export, try to export it as a DBC archive. And if you do, it will be DBC is the Databricks zip format, if you want. If you zip it as an archive, you can just go to your newly created, or if you have an account created under Databricks community account, and then you just upload it again, import it again. So let's say we export this. Let me just show you. So let's see, I do this. Export archive. I don't know how big it is, though. All right, so let's see. Yeah, wow, okay. So I exported this. Then I can do create folder, temp. And in here, I can do import. And then if you're using Chrome, you can just drag and drop like this from the tab. And this is how you move the files or the code from outside Databricks and then import them back into Databricks as well. So you have a month for this, and you can move the code around and play with it. Again, you have my contact information on LinkedIn and my email address. If you want to reach out to me with questions, and I'll be more than happy to at least try to answer them. You know, otherwise I will make sure to route them to the right people. Let's see here. So what we didn't cover today was we did 60. We didn't do 65. right? So I'm just going to run through this quickly. We're not going to do them, but I'm just going to go through what they do. At least you get an idea of what they do. So here, we are using the famous MNIST data set, like handwritten recognition type of thing, right? The digit recognition. And we try to use the decision tree to see if it can classify that. So we have a bunch of numbers in here, like here. And then we try to see if that works good using a tree, which is not obvious because those are like 256 pixels, right? So we're trying to use a tree to see if it can recognize those 256 pixels. Along the way, we try to see what if we reduce the number of pixels. So instead of using like a gray shade, we use just a binary pixel, 0 and 1. Would that have an impact if we switch down to only 2 bits instead of 256? Then we try to run the tree and see if we can do the max depth, not through cross-validation, but manually. Can we create a bunch of models in there and change the value manually, run it, and see what the impact would be for that? So this is what Notebook would do. We changed also the max bin from 256 to 2.
How many classes are you doing? 10 classes?
How many classes? What do you mean by classes?
How many digits are you trying to recognize?
Oh, I think like 10, like 0 through 9 or something like that. Then we try to use a perceptron, which is kind of like a neural network, but it's the easiest one of neural networks, right? Just one easy perceptron. Because you are limited in resources, obviously, you cannot go wild on neural network. I think all you can do here is just one hidden network, layer. Basically, you just use a perceptron with one hidden layer, and then you will see if that can can recognize those digits better than the decision tree. So that's what 65A is. Basically, just running the multi-layer perceptron classifier in there. It's not a big deal. And then here, 75, tuning with Spark Grid Search. So in 65, you would create those manual tuning, right, that we did before. In this one, you will do it through cross-validation. So you will provide the grid search, and you will ask cross-validation to do it for you, exactly like you did in the bike share notebook, right? But I just thought like maybe if I give you to do the 70 on your own is better because that can recaps everything that we should know about in Spark ML. So that's what 75 is. And as you can see here, basically you will have to replace this with this new code here where you have this new pipeline. You just stick in there the indexer and the DCT, and then you create this param grid builder. In this case, then it takes in max depth 4 until 8. And then you create the evaluator as we did before. You create the pipeline for cross-validation, and then you call the fit on it. So that should be kind of very familiar to you guys by now. Now, 75A is the solution, in case you don't want to think about the solution, right? So this is where you would go and then just copy and paste, like if you're tired about thinking about how to do it. So it's kind of like a good way of cheating. So as you can see, we put all the stuff in here. And data set mounts, we didn't need to do it because it was done for you. Now, if you are on your own, like you have your own Databricks accounts, like in the future, you will have to do stuff in here. You will have to mount. Let's say you have a data scientist that creates models or data, whatever, and puts it on S3. If you want to use those buckets, you will have to mount those buckets through DBFS. And this is where you should go if you want to know how to do it, at least, So this notebook will show you how to mount the S3 buckets into DBFS. there is a Python section which is exactly like a duplicate of what we covered today in Scala, right? And just Python for those who don't like Scala and want to use just Python, which I can like understand too, you know. So the code is there for those guys. You have a Python guide for those who don't know Python and want to learn Python. The same thing for Scala. You have a Scala guide as well with all the documentation in here. You have even a Scala cheat sheet. Maybe that's not the word, but Scala is definitely better than Python when it comes to supporting feature on Spark. So every time something comes up on Spark, it is implemented in Scala and followed by Python. See, if you look at it that way, then probably Scala is better than Python in that sense, yeah. But then if you're willing to wait, then it will always catch up with Python. Right. R? I would say probably slower than Python, definitely slower than Python. I don't know. I mean, I don't know why though, because I mean, R is so popular out there. But it looks like now it's gaining momentum in Spark, and people are porting more and more the R stuff on Spark. Okay, so this is all the content that I wanted to go through here. And if you don't have any questions, I was thinking like maybe I can fill you in with more detail about, especially for DevOps people, you know, like how does it look, how Spark looks in the environment, you know. What if I am using AWS and I want to talk to Databricks? How can I do that? Is it even possible? And the answer is yes. Databricks has RESTful APIs. Anything we did today through the GUI, you can do it through REST APIs, right? So you can, for instance, you can call in to Databricks. For instance, let's say you are creating a jar file for a Spark application, right? Let's say you are using IntelliJ, which I personally use and like better than Eclipse. I used to be an Eclipse user. I switched. So let's say you create your stuff in IntelliJ, and let's say you use SBT. Who knows here? Who here knows about SBT? Yeah. So SBT is a great tool, which is really stands for Simple Build Tool. Can't beat that. It's like Maven, a very simplified version of Maven. So you create the jar file, and you want to call Spark on it. And usually what you do, if you are in a production environment, you use something like Spark Submit. And then you pass in the jar and the class inside that jar. And then if you use SBT, you can even instruct SBT to bundle all the dependencies for you. Now, let's say you have a jar. Let's say you are in AWS environment. Sorry for the Azure guys, but I'm sure that you can do the same thing. You put the jar. Let's say you put the jar in S3, right? And then let's say you want to do this. You're trying to do a CDCI, a continuous development, continuous integration. So you have the software engineer checking in something to Git. And I have a Jenkins server somewhere that picks up that change, and I want Jenkins to build the jar based on the new check-in from the software engineer, and I want Jenkins to put the jar in S3, and I want S3 to trigger something that calls something on Databricks to test it. You can do that. So here's how you would do that. So let's say you check in something to Git, and then you have the Git that triggers Jenkins. Jenkins will build a jar, a fat jar or an Uber jar, and then it will put that jar into S3. You can configure S3 to trigger on a put, right? So you can configure S3 to trigger on a put, and then when that happened, S3 will call a microservice like Lambda, AWS Lambda. So it calls AWS Lambda, and then what you have to do, inside AWS Lambda, you can put your code. You can use things like Node.js, you can use Python, you can use Java. And then in that code, you can call the REST APIs that I'm talking about. So you can call things like, I want you to copy this jar file to Databricks. And I can even do more than that. I can just not just copy it. I can add a version number to it while it's in Databricks. And then I can run it in Databricks. And the way usually you use Databricks if you're using the RESTful API is through this tab called Jobs. Because this Jobs is really like cron jobs. So you can create jobs here. You just give it a name, like demo if you want. And then you can set whether you want to do a select notebook or a set a jar. So in this case, you do a set a jar. And it will add the version number, and it will do the set a jar. And then you can tell it which cluster you want to use with that one. You can even create a new one or use an existing one, right? Like in here, we have this one here that I have, that I have been using, right? So if I do this, and then I can set the triggers. I can do every minute, every hour, every day, every week, and things like that. And when that happened, the job will run automatically for you in an automated way. Right. And then you can go in there under the job tab and look at the logs, what happened, were there errors, things like that. This tab is also important when you try to create dashboards. So let's say you create a Spark streaming application, which is running all the time. And then what do? Instead, let's say you want to give the URL link to a boss who happens to be non-technical. Then what you do, you create a dashboard, and then you link that dashboard to this tab, and you just give the link to someone. It's exactly like things like Tableau or things like that, when they just visit the link, and then they can see that updating. All right, so that's what I had to say. Unless you have questions for me, then we'll call it off and done. And I really hope you enjoyed today. And again, if you want to reach out to me, you have my contact information. Thank you.